know some people in this classroom. When we go through and look at SO3, one of the very first things that I noticed that everybody reflexed into doing, which isn't necessarily a bad reflex, particularly as we move later on in the semester, is they immediately started going through and saying sulfur, then you're drawing all your atoms around it. That's not the first step.
I guess the most electronegative.
Nope. Count your electrons. You need to know how many electrons go into this drawing, which means the very first thing I should have seen written by everybody was numbers, not letters. Okay? When we're looking at a Lewis structure, the point of the Lewis structure is to see how the electrons are distributed within that molecule. Okay? If you start drawing the molecule before you have the electrons, you're missing the point. Okay? So how would we backtrack that out? Depending on how you wanted to do it and notate it, okay, I would get aggressive in the notation. Sulfur comes in with how many valence electrons? 6. We're hearing that as kind of a general chorus. How do we know it was 6? Just in case somebody missed it. Our valence electrons are identified off the periodic table. It's the Roman numeral on top of that individual column. Everything underneath it has the exact same valence electrons. Okay? So we want to be able to lean into that. More than likely, you will stop referencing that because you will start just straight up memorizing it, okay? Which is going to happen whether you want it to or not, okay? Yeah. Once you have your valence electrons, we should total it. How many total electrons we have, if we do math right? 24. We now need to figure out where to place those electrons, and associating with the atoms makes sense, but we have to figure out our overall structure. Again, this is a little bit of a crutch because we're looking at not organic structures right away. We would place our least electronegative in the middle, get our oxygens. For those people being like, isn't that where I started the last time? Why'd you give me such a hard time if that's a valid answer? The process by which you get there is very important. Okay, did I do the whole 4 example? The answer is 4. Does that mean I know how to multiply? No, because if I did 1 plus 3, I get 4. That doesn't mean I know how to multiply. Okay, even though 4 is the right answer. Make sense? Right. Next thing that I saw really, really commonly was people dropping this in. Also immediately when we go, oh, what are you doing? Okay. What I think is happening in that scenario is if you've seen something like this before, you start drawing the answer that you've seen, but you don't know why you're drawing that answer. This becomes important because as we move through organic chemistry, we'll change structures around, and we can change structures in such a way that if you reflex into an answer, you get it wrong. Okay, so you have to understand the process by which we would navigate this. So we want to distribute those electrons, again, very painfully. I want to place those electrons on the most electronegative element. Okay, this is going back to the principles of what these definitions mean. Electronegativity is the ability to attract bonding electrons. If you were ever told it was the ability to attract electrons, they're wrong. It's not the definition. The ability to attract bonding electrons is electronegativity. So what we're doing is looking at how the electrons disperse around these individual atoms in this molecule. Now we're okay to look at electronegativity. Okay? So I would start placing them on the most electronegative. Oxygen is the most electronegative, so I should have that trend in mind. I should already have that trend in mind because one of the good things out of that very first lecture was that it told you 2 very fundamental pieces of information that you needed to have memorized as far as trends off the periodic table.
The shells, first of all.
And
then electronegativity.
Electronegativity, and then size, which might be where you were going with shells. Okay? Those are 2 very important trends that we will constantly come back and reference. So if you don't have those trends nailed down and memorized, it's going to be very difficult to apply that trend later on. This is one of those cases of applying that trend. Oxygen is more electronegative than sulfur. We can start placing the electrons. I like to place the electrons between the atoms because I know eventually I'm going to have a bond because it's a molecule. 2, 4, 6, 8. Why do I place 8? Okay, it's an octet. I saw a lot of people counting it out as 6, or for the sulfur, they were doing 6. Okay, and what you were doing is placing valence electrons. This is not valence electrons, this is bonding electrons. At bonding electrons, we get to 8. Octet rule. Okay, that's 8. I need to continue placing electrons. How many have I got placed? 24. How many did I need? 24. Yippee-doo-dah, we're there. We've placed all of our electrons. Anywhere we have electrons between atoms, we can turn into a line to represent the bond connecting those atoms. This is why this question gets pushed, because some of you may not have reviewed those videos, okay? And so what you're relying, oh, Lewis structure, I knew Lewis structure, I learned it in Gen Chem, and this ends up being where you stop. Is this correct? No. Why is it not correct? Okay. Theoretically, you shouldn't have stopped even based off your old training, but again, it comes down to how much you were trained and how much practice you had. You probably didn't get a lot. Okay? Octet. Sulfur needs the octet. To get an octet now, we have to move electrons to satisfy octets. Okay? What electrons do we move? We're going to move the only electrons we've got access to, which is going to be the non-bonding electrons or lone pairs. I try to say non-bonding, but I'll oscillate back and forth. Okay? And I want to move those so that sulfur gets an octet. So I'll take this pair, that was on the right side oxygen, and I'll put it on the sulfur. Does that fix my sulfur?
Yeah.
Careful. Yes, it does. The sulfur has an octet, but it's a bad idea because the oxygen is now wrong. Okay? So what does that mean I should do? I need to change the location of that pair of electrons in such a way that both the oxygen and the sulfur are okay, which means they need to be able to share. I could place it in the space between the atoms. I now have a pair of electrons between atoms, and now I have a bond. Okay? I got people stopping here. Better, also wrong. Why is this wrong? Okay? Which pair of electrons could I have moved? I could have moved it from the right oxygen or the left oxygen or the top oxygen. Because I have all of those options, I have to draw them. That, my friends, is resonance. That's not particularly pleasant, but that's how organic chemistry works. Okay? The reason we make you to go through and do all these drawings is so you start to get an idea of the flow of how electrons can shift through molecules. Okay? And we'll look at that flow in a second. I just realized unintentionally, this one is a fantastic example because I can say we're wrong like every time. It's amazing. Welcome to my world. I get told I'm wrong all the time. No? Okay, I thought it was funny. So cool. Let's push a little bit on this content because we want to talk about the flow of this. How we generated this is we started with that initial structure with the sulfur with the 3 bonds, and we just said, where do we move the electrons from? We just did it. Okay, we just erased and we did it. Let's actually start to bring in the concept of flow. The electrons can move. So I want to start from that top structure, and I want to figure out how to become this bottom left structure. What do I do? Right. And this becomes fun. Well, what's the difference between those two drawings? I need it said louder. Okay, cool. Okay, cool. The biggest thing that people will jump on is the double bond moved. Okay? Yeah. But how did it move? And when people are saying the double bond moved, okay, so everybody's heard that word now, right? We understand it. What do you think that means we're doing? So if I was to draw on this and show how these things moved, what do you think that means?
One bond break. The other one is
True. What does it mean that the double bond moved? Right? The double bond went from there to over there.
It's
Isn't that what that means?
Is it the orbitals? Like
You don't even have to open that can yet. That's next week. Does that make sense? Do you think that matches what we understand for the double bond moved? Okay. Problem with that is no, that's not how it moved. Okay. We start to hyper-focus on the solid things, which makes sense, and we don't focus on the invisible dots, our electrons. Everything we do in OChem is electrons and dots. We must move the invisible. So instead of looking at this as I'm moving bonds, what I want you to do is to think about this as moving electrons. You can still go ahead and grab those electrons, but where do you think they moved?
There's lone pairs on the sulfur.
There's lone pairs on this sulfur?
Well, the P,
That one?
that P bond moved just to the sulfur now, not connected to oxygen.
So there should be a pair of electrons on that sulfur.
Yeah.
Does it have a pair of electrons?
Oh, yeah, it does. No?
They're not drawn. They aren't there. Where did that pair of electrons move?
back to the oxygen.
That pair of electrons moved from the bond to the oxygen atom. We didn't move bond all the way over to the other side bond. We went from the bond to the atom. This does create problems for our sulfur, because now what happened to the sulfur? It's missing its octet. So what else would have to happen?
The lone pair on the other side goes.
Those two arrows, taken together, describe how I move from this top structure to the bottom left. Okay? And so when we're talking about moving electrons in resonance, we can look at it from the standard kind of Lewis structure format at the very beginning and just how we build out our structures and draw them. But eventually what you're going to be responsible for doing is starting from a structure, how can the electrons move? And it dictates and changes the ability for that molecule to react in a variety of different environments to different conditions, all those things. But if you don't understand the basic fundamentals of how the electrons move, you've got problems. Does that make sense? Okay. So there's some big principles that we need to nail down. Electrons move from a source, lone pair, to some place where they're missing. Okay? This first arrow wasn't obvious that they were missing until we looked at the other arrow, right? So it depends where you're looking, and we're running it all simultaneously within that process. Do we have to run it simultaneously? Could I have done that arrow first? We'll call it blue. And then added an arrow to go from here to here? Yeah. Now it's going to come down to, does that mean all of those structures are resonance structures? And we now hit really gray area, wishy-washy space. Okay? And at least initially, one of the things that we try to push is that you're trying to draw resonance structures of equal energy. So is that blue structure of equal energy to our other ones? Why not?
Because the sulfur octet isn't satisfied.
Our colorful black, red, and orange ones all have satisfied octets. The blue one does not. So the blue one can be used as a form of work for you to understand how to navigate it, but it shouldn't be used as an official answer for this is a resonance structure.
Is this what you would call an equal Lewis structure?
So then when we push even further into it, we run into this concept of best and useful. Okay? And I would argue that yes, that blue structure ends up being a useful structure. I now know something about the chemistry of this molecule because that structure is the first worst resonance structure. All three of these are identical. They're all great and grand. That one is the next step down from it that isn't great and grand. But that one helps me to understand how the molecule reacts. How does the molecule react? What's the problem with that structure? We've already addressed it. What's the problem with the blue structure? The octet. So how's this molecule going to react? It's going to react with something that it can steal electrons from to satisfy the octet on that sulfur. That's why that structure is now useful to me. It may not be best, but it's useful. Kind of, sort of? Cool. So let's go back to our lovely resonance structures that we've drawn here. I think we've covered some pretty cool stuff. Is that the answer? Of course not. What's wrong with it now?
Formal charges are I guess, all same for those three, just in different places.
Well, if the structures were all equivalent resonance structures, they needed to all be the same charges, okay? But we haven't defined formal charge. Is formal charge critical? Yeah, it helps put up a giant red flag that this is a potentially reactive atom, right? So it is important to go through and define the formal charge. Your formal charge is calculated based off of valence electrons minus the number of non-bonding electrons minus the number of bonds. You may have heard a variety of different formulas for this. Ultimately, as long as you get the formula right, it doesn't matter. Right? So if we take a look at our first oxygen here, oxygen has 6 valence electrons minus the non-bonding electrons. How many electrons are not in bonds? 6. How many bonds? 1. That gets me a formal charge of -1. I don't have to calculate it for the top one because it's the exact same system. Right? I could go through and look at it for the right one, and what I would find is it comes in as neutral. I don't have to specify the neutral. In fact, people get obnoxious if you specify it as neutral. If we go through and look at the sulfur, what happened to the sulfur? You're like, well, it had its octet. Why do we care? Sulfur has how many valence electrons? 6 minus 0 minus 4 equals +2. That charge needs to be specified. So now when I'm considering the reactivity, these charges could equally help me to understand how the molecule would react. I have negatives on the oxygens. They could donate electrons, but I have a massive positive charge sitting on that sulfur. So is it now correct? What's wrong with it?
Minimize the charge.
I can minimize the charge. You mean I could take this even further? Yeah. I could minimize the charge by taking a pair of electrons off of one of those oxygens and moving it in to share with the sulfur. By moving it in to share with the sulfur, what happened? I heard a bunch of wrong answers. It didn't become neutral. Or the oxygen, yeah, fair play. The oxygen became neutral. The sulfur became +1, and I have a double bond. That oxygen's there. I could do it on the other oxygen and I could get this. Cool. Why did we make those bonds? Why did we make those double bonds? You have the answer.
Sulfur has an expanded octet.
Nope. To satisfy the formal charge. That's why we made the double bonds. Not because sulfur can, because sulfur doesn't always. Right? So it's not forced to do it, it can do it. The reason it does it is to satisfy charges. Why did we make the first double bond? To satisfy octet. Interesting. Octet trumps charge. Get your octets fixed first, then worry about your charges. Right? I could keep ranting and railing about this, but I should stop. If you got more questions, you can come up and ask me or raise your hand and I'll come back to you.